What if I gave you an equation like this? So how would you solve this equation? X squared plus 1 equals 0. So how would you solve this equation?
I mean, it will be x equal to square root of minus 1.
Okay, good. So leave it there for a minute. So you're going to take away 1 from both sides, aren't you? And then you're going to take the square root. So it should be that x is equal to, technically plus or minus, square root of negative 1. Let's just focus on the positive root for the time being. Okay. Now let's have a think about this. Is this possible? Can you take the square root of a negative number? Why not? Well, let's think about it. Rather than just accepting what we've been told, okay, let's actually question it. Let's think like a mathematician. Let's think. We usually think of square roots as a number which, when you times it by itself, gives you that number underneath the square root. So, for example, the square root of 9 would be equal to 3, because if you take 3 and you times it by itself, you get 9. Okay? So what you're really thinking of is this thing. You're really thinking of this thing. Okay? Now, let's think, okay, because now we've got like a negative, so we could think about the square root of negative 9. Would that be negative 3?
No.
Why not? What's negative 3 squared? It's positive 9, right? So that no longer fulfills our definition of a square root, something which you times by itself to give you that number, okay? So the question is, how can we deal with the square root of negative numbers, given that every single number that we've dealt with up until this point won't find us the square root of a negative number, okay? So the solution is just give this a name. Let's imagine that there is a number that is equal to square root of negative 1, okay? In other words, a number which, when you times it by itself, gives you negative 1 by definition. And we call this number I, okay? Does anybody know why we call it I?
Because it's imaginary, or?
It is, because it's imaginary, okay? Because it's imaginary. So we have to kind of imagine, because all of the real numbers, all of the numbers that we feel comfortable with, because all of these numbers we feel comfortable with, like there's some version of them which exist in nature, okay? Particularly like pi and e and things like that, they all exist in nature. Now we've got something that kind of breaks the real world, right? There's no way of finding the square root of a negative number using all of these numbers. So we have to use our imagination a little bit. In actual fact, imaginary numbers was kind of, it was coined because in the sort of 1800s, or the 1700s maybe, I can't remember quite when, they used to have competitions to solve equations, okay? And specifically, they used to have competitions to solve equations like this, so cubic equations. And they used to kind of say, right, whoever can solve this the quickest, so they used to walk into a room, maybe filled with all these mathematicians, they kind of gave them an equation, whoever solves this quickest wins the competition, okay? And obviously people had different ways of solving this equation, and one of the ways is by coming up with a formula. In fact, there was a guy called Gauss, and I think there was somebody else as well who was kind of his apprentice. Very famous mathematician, by the way, very, very good mathematician. He came up with the fundamental theorem of algebra, in case you're interested. He came up with a way of solving this, and it was similar to using the quadratic equation, okay? And actually, if you're going to use this, there was a bit of it that involved using the square root of a negative number. So what they said is this bit here doesn't really make sense, but just imagine that you can do this, that you can take the square root of a negative number, and then it all falls out in the wash eventually, right? So that's where the phrase imaginary numbers came from. You had to kind of imagine that it exists, even though you know that it probably didn't, okay? But let's have a think. So what we now have are not imaginary numbers, but complex numbers, okay? So with a C there. Let's have a think, okay? So this at the moment is our real number line. In fact, let me draw it over here towards the right-hand side. Okay, so this at the moment is our real number line, okay? So we've got 0 in the middle, and then all of the numbers filled in each side. So that's what we've gradually been doing as we go along. This is the real number line, okay? If I want to think about this geometrically, I haven't got any more space for the imaginary numbers. There's no way that I can put them anywhere along this number line. So where do you think I'm going to put them instead? I can't put them on this number line, okay? I'm stuck. That's all the real numbers. There's no way that the imaginary numbers will also fit in along there. But have a think. I've also got all this space above and below the number line, haven't I? So why not make use of that? If I make use of that, I can then represent my imaginary numbers in combination with my real numbers. They kind of go off at a tangent, okay? They go off at 90 degrees. So this here, above and below the number line, would be my imaginary number line, okay? So this would be my imaginary number line. Let's change that to real. Okay? So for example, this works in exactly the same way as my real number line. Okay, so if I wanted to represent 1i, it would be about there. If I wanted to represent 2i, it would be about there. 3i would be about there. If I wanted to represent root 2i, it would be about there. Okay, so it works in exactly the same way as my real number line. Same with my negative numbers. So negative I, negative 2i, etc., etc., etc. Okay, works in exactly the same way. It's just now I'm making use of that two-dimensional plane. Okay. Now, what's really cool about representing them like this is that I can think about them as a combination of real numbers and imaginary numbers. Okay? If I think about combinations of real numbers and imaginary numbers, then I get myself a complex number. Okay? So the word complex does not mean it's difficult, right? The word complex simply means you have an imaginary part and a real part. All the other way around. Maybe I write the other way around.
But Alex,
Yeah.
How come these complex numbers are joined into literature of mathematics? Because other than say I would imagine such a number in theory, and then you say, and then I solve a question, so equation with that number. That means I found a new type of number or something, or? So
that's a really good question. So this is why at first, when they first kind of came up the concept that you could take the square root of a negative number, people were going, well, why? What use has that possibly got? That's your question, right? Mm-hmm. Well, as you'll see, and we will hopefully see, they are really, really useful, okay? Because now suddenly numbers are no longer one-dimensional. They're no longer just a flat number line. They're actually two-dimensional, okay? So for example, let me just put some numbers in across here as well, just to help you out. Okay? For example, let's say I wanted to represent the complex number 1 plus 2i. So my real part is worth 1, and my imaginary part is 2 lots of the imaginary number square root of negative 1. Okay? So the number 1 plus 2i, I could represent as moving 1 across and 2i up. So this here is 1 plus 2i. Okay? But look at that. It's a number. It's a number. Okay, but numbers are no longer one-dimensional. In other words, they have a unique spot along the number line, the real number line. They're actually two-dimensional. Okay, they're two-dimensional. Okay, and if you think about it, every single real number is also complex. It's just the imaginary part is what? 0. You happy with that? Yeah. Mm-hmm. So let's add to our circle then. Right the way around here. So we've got all of the real numbers contained in this circle. If we want to add more, we can add an extra one, the complex numbers.
But,
Yeah, go on.
Well, I was going to say, is it possible to have such a number which have like 3 dimensionals?
Yes, absolutely. Yeah, and actually, this is not the full set of numbers that we know. There are actually extra numbers called quaternions, okay, and then we've got octernions beyond there, and actually I think there's a few more beyond there as well, okay. But yeah, you're absolutely right. If you want to have now 3-dimensional numbers, you'd be then looking at quaternions, yeah, and 4-dimensional numbers as well, which is again kind of quite interesting. But for the moment, let's just focus on the 2-dimensional numbers, which are complex numbers, real part plus an imaginary part. Does that make sense? Everything we've done there? Yeah.
Very rational.
Exactly. So in other words, every single number that you know now, stop thinking about numbers as one-dimensional. Stop thinking about numbers as one-dimensional. In actual fact, they're two-dimensional. Okay, they've got the up and down part. It's just all of the real numbers that you're familiar with, like e, pi, -1, -43, a million. It's just they're represented along that one-dimensional number line. There's no imaginary part to them. Is that okay? Good, fantastic. We give this thing a special name, where we've got the real number line across here and the imaginary number line up here. Then we can move in that 2-dimensional plane. 2 names we can give it. We can either give it the complex plane. That's one name for it. Okay. The other name that we can give it, and it was named after the French mathematician that came up with it, the Argand diagram. So Argand was the guy that came up with it, or Argand, I think. Diagram. Okay, so there's two names that you can give this thing. You can either give it the complex plane or the Argand diagram. Either one of those is fine.